We can work the previous problem using vector operations. We have our airplane, and our airplane has an airspeed of 430 miles per hour on a bearing of 135 degrees. So a bearing of 135 degrees, if we want to write that as a standard angle measured from the positive x-axis, would be the angle 135 minus 90, which would be negative 45 degrees. So a traditional direction angle, theta, is negative 45 degrees, or we could also say 315 degrees if we measured the other way around. And we want to take this plane and we want to write it in component form as a vector. And so what we know is that x would be equal to the magnitude of the vector, which is 430, times the cosine of the direction angle, which is negative 45 degrees. And y would be equal to 430 times the sine of the angle, theta, which is negative 45 degrees. So in component form, our plane is the vector, if we multiply this out, 304.056, negative 304.056. So now we need to look at our wind. And what we know about the wind is it's blowing 35 miles per hour in the direction of north 30 degrees east. So north, turn 30 degrees to the east. If we think of this as a normal angle in standard position, theta would have to be 60 degrees, because 90 minus 30 is 60. And so to find our wind in component form, x would be equal to 35 times the cosine of 60, and y would be equal to 35 times the sine of 60. So our wind, written as a vector in component form, is 17.5, 30.311. So our resultant would be equal to the plane vector plus the wind. So if we take our plane, which was 304.056, and add it to our wind, which was 17.5, the result would be 321.556. If we do the same thing for our y component, we take negative 304.056 and add that to the wind, 30.311, we'll end up with negative 273.745. So this is the resulting vector of the plane with the wind added to it. So the speed is going to be the magnitude of this resultant, and we can find the magnitude by taking 321.556, squaring it, plus negative 273.745, squaring it, and our wind speed, or excuse me, airspeed turns out to be 422.297 miles per hour, which is the same answer as we got on the last example when we reworked this problem using law of sines and law of cosines. All right, next we need to find the direction that our plane is actually going. And now that we have our resultant vector, notice that it's 321, negative 273. So we've gone 321 to the right and down 273. So this is our resultant R, and we're wanting to find either this angle theta or if we want to write a bearing, we would be measuring from the north around to that resulting line. So we can find that using our tangent function. This would be our x component, and this is our y component. So the tangent of theta would equal y over x. And I'm going to ignore that negative for a moment and just get the reference angle. So the tangent of theta would be 273.745 divided by 321.556. So using arctangent or inverse tangent on your calculator, we get that theta equals 40.408 degrees. So that is this angle theta. So we could say that our direction was negative 40.408. We could say that our direction, if we want to give a standard angle, is 360 minus 40.408, which would give us 319.592 degrees. That would be this angle, measure that direction. But if we want to write it as a bearing, like we did on the last problem, then that would be the angle measured from north down to our resultant. So that would have to be 90 plus the 40.408 degrees, which would give us a bearing of 130.408 degrees, which is the answer we got when we worked it using law of sines and cosines. So this is a totally different way to work the same problem. That's why math is such a great subject, because you can choose whether you would rather use law of sines and cosines to work the problem, or whether you would like to write the situation in terms of vectors and use vector operations to work the problem.